Okay, so let's continue. In the previous segment, we began looking at the strong form of the problem for linear elliptic PDEs in 3 dimensions with a scalar unknown. Right? We wrote out the strong form. We wrote it out in coordinate notation. Learned a little bit about the quantities that show up, and the very last thing we did was make a connection with the physical problem of heat conduction at steady state. Let's carry on with this, and what I want to do first in this segment is, for completeness, also make the connection with mass diffusion in 3 dimensions. Okay, so just as we looked at heat conduction, let us now consider the problem of mass diffusion. Okay, of course the strong form is the same, so we're not going to rewrite it. Let's just say what the variables would translate to here. U in this case would be a concentration, right? The concentration of some field. Right? Now it could be a concentration either in terms of mass per unit volume, or maybe number of particles of a certain kind per unit volume, right? So this could be a concentration in terms of mass per unit volume or number per unit volume. Or it may even be normalized by some reference concentration to be rewritten as something called a composition, right? So I'll just write this here. Composition is essentially a reparametrization of the composition that's often used in physics. Okay, so that's what U would be. All right. What about J? Now that we know direct notation, it's safe to use to just do that, right? J in this case would be the mass flux, right? The mass flux or the number flux, right? Which would be mass flow perpendicular to a unit area per unit time. Okay, or alternately, if we were doing number flux, it would be the same sort of thing, right? We would be talking here of the number of some particle flowing perpendicular to a unit area per unit time, right? So number of particles flowing perpendicular to a unit area, and so on. Right? You can complete that statement. All right, so that's what J would be. Our constitutive relation, J equals minus kappa. Now actually I realize that this is probably the very first time I'm writing the entire constitutive relation in direct notation. Okay, so the way we would write a temperature gradient would be that, right? Nabla being the spatial gradient operator. Okay, it would be this, or perhaps you are familiar also with writing that gradient as partial of u with respect to the vector x. Okay, so if we had this constitutive relation, kappa then would be the diffusivity tensor. Okay, and as we did in the case of heat conduction, we would make the observation that kappa equals kappa transpose. It's symmetric and it's positive semi-definite, right? So if C not equal to 0 and C being a vector, right? If C is a non-zero vector, then C dot kappa C is greater than or equal to 0. Okay, so the same mathematical properties as the heat conductivity tensor. All right, and then the condition that U equals UG would simply be a condition stating that we are controlling the concentration or the composition, right, on the Dirichlet boundary, right, on the specified subset of the boundary. And finally saying that minus J dot N equals J sub N on partial of omega sub J would be the mass influx boundary condition. Okay, so everything else is well, everything is really the same between the heat conduction and the mass diffusion problem in 3D. Okay, at steady state. It turns out actually when we take away the steady state assumption, also there is this analogy between the two. And of course, the equations will be the same. We will study those equations as well and develop finite element methods for them. So, okay, so at this point we've looked at the strong form in coordinate notation. We've also looked at some direct notation. Just for completeness, let me write out the PDE of the strong form in fully in direct notation. Okay. Okay, so this is find U given U sub G, J sub N, F, and the constitutive relation J equals minus kappa grad U. Okay, find U given all this stuff such that now J I comma I is essentially the divergence of J. Okay, so we get minus del dot J, right? And del dot is the divergence operator in direct notation, equals F in omega. Okay, the boundary conditions, the Dirichlet boundary condition is straightforward because it's only on the scalar unknown. U equals U sub G on partial omega U, and the Neumann boundary condition is minus J dot N equals J sub N on partial omega sub J. Okay, right, and this actually is it, right, for as far as our strong form is concerned in direct notation. Okay, and one useful thing to look at here is what happens to this equation when we make the substitution of the constitutive relation, right? So when we make the substitution, we so substituting J equals minus kappa grad U in the PDE, right, we get minus del dot minus kappa grad U equals F, right, in omega. Okay. And then something that's commonly done is that if kappa is spatially uniform, right, so that means kappa is not a function of position, right, what this gives us then is the following equation, right. It gives us minus del, I'm sorry, it gives us, if kappa is uniform, it tells us that we get kappa contracted with the Hessian of U, okay, this equals F, right. Now, it's useful to write this in coordinate notation to see exactly what is meant here. That the double dot there, which I've referred to as the contraction, essentially is an extension to tensors of the idea of a dot product, right. And what this thing is doing for us is it is doing kappa ij multiplying ui comma j. Okay. In this context, what we have here, that is the Hessian operator. Okay. We could also take the special case, which is often done, which is that which is to assume or to consider cases where kappa ij is it can be written as a scalar kappa multiplying the Kronecker delta, okay, sometimes called the Kronecker delta tensor. Okay, when we do this, what it implies for us is that now if we go back to the problem where that we wrote just above, the form that we wrote just above, and here we are noting that not only is the tensor kappa representable as a scalar multiplying the Kronecker delta, but that furthermore here too we are saying that kappa is the scalar kappa is uniform, right. If this thing is uniform, then what we arrive at is kappa delta ij u comma ij, right, equals F, right. And here if you observe what the action of the Kronecker delta is, it reduces that relation, that PDE, to kappa u comma ii equals F, okay, in omega. Okay, right. So this form of the equation is often called the Poisson equation, right. So this is the Okay. In direct notation, the same thing would be kappa. Now del square u. But note that I do not have an underbar on the del square, implying that it's not a tensor. This is just the Laplace operator, right? So del square of u is just the Laplacian. Okay, all we've done is write the Laplacian using that operator del square. Okay, so and of course in this sort of case, if we have indeed that kappa is that the tensor kappa can be represented as a scalar kappa, right? If we say that we have that representation, then for the Neumann boundary condition, right? For the Neumann boundary condition, which is minus j dot n equals j sub n. This essentially reduces to the requirement that minus kappa grad u dotted with n equals j sub n. Okay, it reduces in this case to a requirement on the normal gradient of the temperature. Okay, so this thing is this is the normal gradient of the temperature u. Okay, and these are simplifications that are commonly used. In fact, it is very often assumed that kappa does indeed have this representation via the scalar kappa and the Kronecker delta, right? And what this translates to is that the physical sort of situation that this represents. So if we have kappa equals that, if kappa ij equals just a scalar kappa multiplying the Kronecker delta, what we have is what is called isotropic heat conduction. Okay, we are specifying here that this body is such that when heat is flowing in here, heat flows only in the direction of a temperature gradient, right? So if we introduce a temperature gradient in one direction, it does not induce heat flow in any other direction. Okay, that's what it reduces to. And furthermore, it also says that the amount of heat flow we get by introducing a temperature gradient in one direction is exactly the same heat flow that we get by introducing a temperature gradient in another direction. In both cases, the heat flow vector would be aligned with the direction of the temperature gradient itself, and the amount of heat flow would also be the same if we specified that the same temperature gradient in different directions. Okay, so those are the sort of simplifications that are often used in representing heat conduction, or of course equivalently mass diffusion as well. Okay, we're actually going to end the segment here. When we return and pick up the next segment, we are going to find ourselves ready to look at the weak form of the problem.